Hello guys, what's up and welcome to Nerdsup. So today's topic is nearest neighbor classifier. But before we get going, if you're not checked out my previous video on nearest neighbor classifier, then please go check it out and come back because whatever we are gonna code today is related to my previous video. So if you don't know about nearest neighbor classifier, then go back, check it out. In that way you'll understand what we are coding it today. Okay, and today we are going to perform nearest neighbor classifier on pen based recognition of handwritten digit dataset. Guys, this is a real dataset from UCI website. Okay, and these are its data abstract. So it is 16 dimensional data and all the attributes are integers, and we are going to perform classification on this. Let me just show you the dataset. This is how the dataset looks like. I've stored this in a data file called pendigit.txt. It's a 16 dimensional data where the last column represents the labels, and these are the 16 dimensions. So the guys who prepared this data, they told few writers to write 250 digits in random order inside boxes of 500 by 500 tablet pixel resolution, and from that raw pixels they used some kind of sampling to extract these 16 features, and it turns out that these 16 features are really good 16 features. I don't know what kind of sampling methods they used or or how did they perform sampling, but these are the 16 features that they got. And if you want to know more about this data set, then you can check out the description below. I have the links for this the description of the dataset in the description of this video. So let's get started. So first, of course, we'll import our dependency. We're gonna import numpy for scientific calculation. We're gonna import from collections counter. Okay, and now we're gonna define our k value. K value is gonna be 1, and we're gonna store the pen digits training.txt in a variable called train file. So this is where the training set is there, and we're gonna store the test data set in a test file name in test file variable, and then we're going to define a load data function which will take as parameter the file name, and it will return us the training data. We're going to do the same for the test. So before running the cell, we're going to define this function load data. So we are going to return np.load text. So this is just a one line of code that loads the text from you from the txt file. This is the magic of numpy. This is the power of numpy. So that's it. You just need one line of code to load the data. Let's run the cell. No error. Let's run this cell. No error. Let's run this cell. And yeah, finally we have loaded our data. So let's print our data just to make sure that everything is going correct. We're gonna print the first 5 rows, and yes, it's correct. Now we're gonna create an object of class k and n, which will take parameters trend, test, and k value. But before running the cell, we're gonna define this class k and n def, and we're gonna define the constructor which will have as training data, testing data, and the k value. And now we're gonna define few attributes of this class, that is self.train data, and we want the train data we want all the rows and we want all the columns, except we are going to exclude the last column. And now we're going to define the training label which will have all the rows but only the last column. And same we are going to do it for test, self.test data equal to test data, and we will have all the rows but only 16 columns. We're going to exclude the last column. Now we're going to define the test label where we'll have the test data's all the rows but only the last column. And now we're going to define k, and then we're going to define self.correct equal to 0. This is for classification. Now we're going to define the function normalize. Okay, remember guys, in the previous video I talked about normalization, how much important it is, normalization is when we are using our distance function as Euclidean distance or Manhattan distance. So we're going to perform normalization. So over here, in my previous video I talked about 2 common approaches, so I'm going to use one of the common approach, that is a zero mean and a standard deviation of 1. So we're going to calculate mean for every column, that's for every so np dot mean self dot train data of axis to be 0. Okay, in that way we're gonna calculate the mean of every column, and same we're gonna calculate the standard deviation. So this is just one line of code because of numpy. So axis equal to 0. Yeah, that's it. We calculate the mean and standard deviation for every column, and now we're gonna iterate through each and every column in our training data. Okay, we're gonna iterate through each and every column in our training data so that we make the mean to be 0 and standard deviation to be 1. So yeah, so first we're gonna subtract the training data of the first column with mean of the first column, and then we're going to divide it with the standard deviation, and the same thing we are going to do it for test data. So guys, for test data we use the same mean and standard deviation of training data, and we do not calculate separately the mean and standard deviation of the test data, right? Test data is only for or how good we are performing. All right, we do not get any extra information from the test data. That's it. We just want to know how good our model is, so that's why the test data is there. All right, so yeah, let's do that. We're going to perform the same operation that we did for training data on the test data. So self.test data and divided by standard deviation of that particular column. So we're going to index it with I. Let's run this cell. Everything is going good, no error. Now we're gonna, before that, let me call this normalize function and run this too, so that we make sure. Oh, some error. Look, I thought so. Some error. Cell train data. Okay, let's add a self over there. Let's run this again. Let's run the below cell again. What? Train data operands could not be broadcast together which heaps. There's some shape mismatch which I really don't know. I don't know what went wrong over there. Let me check. Let me rerun this, and same error when I rerun it. Okay, so I think we have to debug this. Let's check it out. What's wrong? I'm not able. Oh, I missed the. Yeah, we had to just put that index over there in the standard deviation. That's why. Yeah, I think now it should run. Let's run this cell. Let's run this cell. No error. Great. Let's move forward. We're going to define a new function called classify that will perform training. Actually, it will perform classification, not training. In nearest neighbor, there is no thing called as training, but still people do say training. I don't know why, but okay, let's perform classification. For classification, we have to iterate through each and every test data, right? We're gonna classify each and every test data separately, and for that we wanna find the distance between the test data and every training sample. So we're going to define a function calculate distance that will take as parameter the particular test data and whole of the training data, and it's going to return us the distance between the test data and all the training data. So distance equal to x minus y, and then distance equal to np dot square, because we're going to square the difference of the x minus y, and then we're going to sum it over across the axis equal to 1, and then finally we're going to take the square root of the distance and we're going to return the distance. So remember guys, the Euclidean distance is we first take the difference, then we square it, and then we sum it, and then finally we square root it, right? And it will give us the distance. Let's run this cell. Indentation, I guess, no colon. Let's run this again. It should be inside the for loop. Let's indent it. Let's run it again, and no error. Let's run this thing again. No error. Let's run this again. No error. Great. Now we're gonna call classify just to see that everything is going good. We got the distance values. Great. I'm gonna interrupt it, and now let's go ahead. Now what I'm gonna do is that I'm gonna perform concatenation. All right, so I'm gonna concatenate the distance and the labels, right? So because we are only interested in the distance and the labels, right? Now I'm gonna make a transpose of it so that it's two columns and all, like to cross the number of test data, and then I'm going to sort it based on the distance, right? We want the shortest distance, so I'm going to sort it so that the shortest distance, so it is sorted based on the shortest distance, right? So this line is going to do that for me, and then finally I'm going to call a function self.showResults, which will take as parameter the distance and the iteration value I. And let's define this function. So what this function is going to do is it's going to calculate the number of times we are correct in our prediction, in making our predictions. Okay, so yeah, let's define this function. So self distance, and I'll take this as a row number. Great. Now if the k value is 1, so we will only extract the first distance, right? So the nearest neighbor is distance self.k, and we want all the columns, and the predicted one will be the k neighbor itself, right? But we're gonna take the test label, so k neighbors of 1, so we want the first column, that's the second column actually, and then true equal to self.test label of the row number. Okay, now we're gonna write the condition, what if the k is greater than 1? If the k is greater than 1, then k neighbors equals to 0 to self.k, right? Because it's going to take first k rows and all the columns. And now out of this k neighbors, we want the most common we want the most common number of classes this array has, the k neighbor array has. So we're going to do that by counts dot most common of 1 and 0 0. That's going to give us the most common class, the samples that are of most common class in the k neighbors. Okay, and now true equal to self.test label of row number, and if true is equals to predicted, then we are correct. So we're going to increment our global variable self.correct, and then we're going to print this just to make sure that everything is correct. So self.correct predictions equal to self.correct. Let me make that correct predictions. Okay, let me run this. Okay, no error. Let me run this again. No error. Let me run this, and there's an error. Too many indices for our array. I don't know. We have to check it out. What's wrong? Let me print the value of the distance, because it says too many indices. So let me print out the value of the shape of the distance. Let's see. Then print the value of the shape. That's weird. Distance.shape equals distance.shape, comma, I forgot a comma. Let's rerun this as well. So this time it did print, and it's a 1D array. It should be a 2D array. Okay, what went wrong? Let's see. I don't know what went wrong. This is tough. Oh, there should be train labels. We passed test labels, it should be train labels. Now this should run. Now this should give me, okay, great, it did give me output, right? It did give me the distance and the correct predictions. Great, so we are on the right track. Great, so I'm just gonna comment this, and now we're gonna write the code for displaying the accuracy. So the show ACC function is gonna display the accuracy for us. So print accuracy is equal when k self.k is self.correct divided by the number of test labels we have, the number of test data we have. So self.test label.shape of 0. Now let's run this. Great, no error. And I want to see this. I want to see how many times we are correct, just to, in case if our code breaks. and let's classify. I don't want to print the shape of the distance. Let me comment this. Great. Let's run this. And now let's run this and run this again. Okay. So it's gonna take a while because I don't know, the number of test data is 3000. So it's gonna take a while, and for k equal to 1, the authors of the data, they got an accuracy of 97, so we should also get an accuracy of that. So while it is running, I hope you like this video, and in the next video we are going to compare our results with scikit-learn. Okay, so in my next video I'll be performing KNN using scikit-learn, and we will be comparing and seeing that how good or bad we were as compared to scikit-learn. Okay, and I'm still waiting. I don't know what is happening. Why is it taking too long? It's 3000 rows. Why is it not displaying the accuracy? Oh, we didn't call the show ACC function. Okay, so let me just quickly make a new cell and insert cell below, and over here I'll call the show ACC function. Show, then copy and paste it. Yeah. Ooh, boom! We got an accuracy of 97.45, and that's a really good accuracy. I think the authors of this data set also got the same accuracy on when k is equals to 1, and whew, that feels so good. We perform nearest neighbor classifier on a real UCI data set, guys, and we perform classification on recognizing digits. That's really great. So that's it for this video, guys. See you, bye bye. And yeah, if you like our video, then do subscribe to our channel and do hit the like button. All right, okay, bye, see you, thank you.